Welcome back to The Explainer. Today, we're diving headfirst into an invisible force that literally dictates the physical world all around us. I'm talking about pressure. It's a single, surprisingly simple mathematical relationship, but as you'll see, it governs a massive variety of our everyday experiences. Everything from the sharpness of a kitchen knife to the exact mechanics of how we drink from a straw. Let's get right into it. So here's our agenda for today. We'll start with number 1, what is pressure? Then 2, the 2 golden rules. 3, everyday pressure examples. 4, nature's design, specifically looking at the camel. 5, liquid pressure and depth. And finally, number 6, the invisible atmospheric pressure. All right, kicking things off with section 1, what is pressure? Imagine picking up a heavy backpack and just plopping it down on a table. Gravity is pulling it toward the floor, right? So the bag is physically pushing down on the table with its weight. Well, that pushing effect, that's pressure. It simply tells us how much force is being distributed over a specific surface area. To really wrap our heads around this, think about carrying a super heavy duffel bag. If you carry it by a thin piece of cord, it is going to dig painfully into your hand. But if you carry that exact same bag by a thick, padded strap, it feels totally fine. The weight of the bag hasn't changed, the total force is identical. The only thing that changed is the area over which that force is applied. So it's all about the relationship between how hard we are pushing and the size of the area we are pushing against. And that brings us to the core formula of this whole explainer. Pressure equals force divided by area, or P equals F over A. You're definitely going to want to keep this equation in the back of your mind because it's the exact lens we'll use to decode everything else today. Now, in physics, we measure this in something called pascals. 1 pascal simply means you have 1 newton of force acting on exactly 1 square meter of area. By treating this formula not just as math on a chalkboard, but as a description of physical reality, we can start to see how tweaking either the force or the area completely changes the outcome of an event. Moving on to section 2, the 2 golden rules. Okay, by taking that single formula, we can establish 2 golden rules for pressure. Rule 1, which is super intuitive, is that if you keep the area exactly the same, but push harder, your pressure goes up. Push softer, it goes down. Force and pressure move in the exact same direction. Simple, right? But rule 2 is where things get really fascinating, because it's an inverse relationship. If you keep your pushing force exactly the same, but you shrink the area down, your pressure absolutely skyrockets. You're suddenly concentrating all that force. Conversely, if you take that same force and spread it out over a much larger area, the pressure plummets. It just fades out. This interplay between constant force and a changing area, that's the secret behind so many everyday physical mysteries. Which leads us nicely into section 3, everyday pressure examples. So have you ever wondered why someone walking in high heels sinks immediately into soft grass or mud, but a person of the exact same weight walking in flat shoes doesn't sink at all? Think about this through the lens of that second rule we just talked about. The body weight, the downward force, is completely identical in both scenarios. But that tiny, narrow stiletto heel is touching the ground over an incredibly small area. And because the area is so minimized, the pressure is drastically maximized. That tiny little point generates massively greater pressure, driving the heel right into the soil like a stake. Meanwhile, the flat shoe takes that identical body weight and distributes it over the entire footprint. This drops the pressure so incredibly low that the soft grass can easily support it. We actually weaponize this exact same principle in our tools. Think about swinging a heavy hammer with all your might at a flat-headed metal rod. It's just going to bounce right off the wood, right? Maybe leave a little dent. But if you swing with that exact same force at a sharp nail, it pierces the wood completely effortlessly. Why does that happen? Well, the universe experiences that swing entirely differently based on the tip of the nail. All of your swinging force gets funneled and concentrated right into a nearly microscopic point at that sharp tip. This creates an overwhelming, localized pressure that the wood simply cannot withstand. It turns out we humans have been hacking this physics equation for centuries without even realizing it. When a chef meticulously sharpens a kitchen knife, they aren't just doing it to make it look dangerous. They are strictly, purposefully minimizing the contact area of the blade. They are driving the A in our equation as close to 0 as physically possible. That way, even a gentle slice generates enough pressure to cleanly sever a tomato. And on the total opposite end of the spectrum, think about heavy furniture. We put wide, flat feet on heavy beds, or we strap broad snowshoes onto our winter boots strictly to increase the contact area. We want that A to be huge so the enormous downward force doesn't punch holes right through our floorboards or sink us waist deep into the snow. All right, on to section 4, nature's design, the camel. Now think about this for a second. Shouldn't a massive, heavy animal immediately sink deep into shifting, powdery desert sand? Seriously, if you or I were out in the dunes carrying an equivalent ratio of weight, our feet would punch right through the surface. We would literally be buried up to our knees with every single step. The answer to this mystery lies in their evolutionary design, specifically their feet. You see, nature understood P equals F over A long before human beings ever wrote it down on a whiteboard. Camels have these incredibly wide, flat, fleshy foot pads, and as the camel steps down, these pads flatten and spread out even further. This brilliantly takes their immense body weight and spreads it out over a massive surface area. Just like the flat shoe on the grass or the snowshoe in the snow, the camel is dramatically lowering the pressure it exerts on the soft ground. And that ultra-low pressure is exactly what allows loose grains of sand to support a creature that weighs well over 1,000 pounds. Let's switch gears a bit. Section 5, liquid pressure and depth. So far, we've really only talked about solid objects pushing on other solid objects. Let's escalate our states of matter and apply these same concepts to the completely fascinating world of liquids. Take a look at the extreme contrast in this water tank. Notice how we have a weak little trickle of water just sort of leaking out near the top of the tank, a slightly stronger stream in the middle, and then this powerful, forceful jet shooting way out from the bottom. If pressure was uniform everywhere inside a container of liquid, those three streams would all behave absolutely identically. They'd fall in the exact same arc, but clearly they don't. That's because, unlike solids, liquid pressure introduces a critical new variable into the mix: depth. The deeper you go into a liquid, the more liquid is physically stacked up directly above you, pushing down with its own weight. If you've ever swam down to the deep end of a swimming pool, you have physically experienced this formula firsthand. You know that squeezing sensation, that ache in your eardrums. That isn't just water, that is the literal physical weight of all the water above you stacking up and pressing against your ears. So the fundamental takeaway for liquids is that as depth increases, pressure firmly and consistently increases right along with it. And hydrostatic pressure is solely dependent on that vertical depth. Notice how, despite the crazy, winding, vastly different shapes of these connected glass columns, the water sits perfectly at the exact same level across all of them. The shape of the container? Doesn't matter. The volume of the water off to the side? Doesn't matter at all. Because the liquid is connected, the pressure equalizes based purely on depth. If you're at the exact same depth anywhere in a connected, uniform liquid, you are going to experience the exact same pressure, period. And finally, Section 6, the invisible atmospheric pressure. For a grand finale today, we're going to look at a form of pressure you interact with constantly, but you can't even see it, the pressure of the air all around us. But before we reveal the exact mechanics of it, ask yourself a question that, honestly, most people never stop to think about. What is actually pulling the liquid up against the force of gravity when you take a sip from a straw? I think most of us just assume our lungs are acting like a vacuum cleaner, directly hooking onto the liquid and pulling it up into our mouths. But physics tells a much more amazing and, honestly, counterintuitive story. Here's the wild part. You aren't actually pulling the liquid at all. You are just creating a void. When you wrap your lips around a straw and inhale, your lungs expand and you're simply evacuating the air that was trapped inside that little plastic tube. By removing that air, suddenly the pressure inside the tiny environment of the straw drops way below the normal atmospheric pressure of the room outside. You've effectively created an area of uniquely low pressure. And here is the absolute secret to how it all works. It is actually the massive, invisible weight of the Earth's atmosphere pushing down on the exposed surface of the drink in your cup that physically shoves the liquid up into the empty space of the straw. The atmosphere is basically a heavy ocean of gas, and it is constantly bearing down on everything. Because you've lowered the pressure inside the straw, the normal, heavy pressure outside the straw easily wins the tug-of-war. The atmosphere literally forces the liquid upward to fill the void you just created. So, you don't actually pull your drink, the sky pushes it to you. Which leaves us with this incredible thought to wrap up on. If the invisible ocean of air around us is heavy enough to completely overcome gravity and push liquid up a straw, how much unseen pressure are you carrying on your shoulders at this very moment? The formulas of force and area aren't just abstract math to memorize. They're physical realities working on you and everything around you, every single second of every day. Keep questioning the physical world around you, and I'll catch you in the next explainer.